Hey, my name is Doug Hunsaker, and I'm going to go over a framework that we've developed in our lab here in the last year or so, and just explain how this architecture works. The main point of this architecture is to be able to go rapidly from a concept vehicle all the way to flight testing very quickly. And so we've needed this type of capability for some of the work that we're doing, and so anyway, we've put together this framework, and I'm just going to walk through the process here. So, first of all, you start with a concept. The user brings the concept. This can be anything from a fixed wing aircraft to quadrotors to VTOL hybrid type vehicles. I'm going to show you a graphical user interface we have called Mockup. This is something we developed years ago. It's free and open source on our website, where you can go in and play around with a geometry and basically sketch this vehicle very rapidly. And then there's information about that below here. And then that information gets fed into our physics engine. Physics engine is called MAVIS, and this is kind of a headless code that basically all it does is integrate forward in time once it has a vehicle model. And it can, if you give it a rough geometry like this, it will estimate the mass and aerodynamics just using low fidelity estimates. Or you can feed in higher fidelity information about that model. If you have CFD information or wind tunnel data or mass distributions, moments of inertia, that type of thing, you can feed that into a much higher fidelity. And then this integrates forward in time and is looking for information from a controller. So I'll show you how how it looks for information and how you specify what controls are within this framework. And it's looking for information from a controller. That controller can be written in MATLAB, which many controls people use, or Python or C. Any code that you're using for controls, you can basically link to this and send in real-time information to control the vehicle. And then the outputs of that vehicle can be viewed graphically. We've got two internal graphical viewers that we've developed. One of them is in Python. It's very simple, and I'll demonstrate that today. Another uses Unreal Engine, which is, the graphics are gorgeous on it, but both of them operate in the same principle. They're just reading information from MAVIS, which is sending the information out in real time. Now, this framework can be set to run real time or faster than real time or slower than real time. We've had a couple situations where the controller is slower than the physics, and so to test out control algorithms or theoretical algorithms, the physics engine needs to wait for controls information, and so that capability is built in, so it can run faster, slower, or real time. Another thing that MAVIS can output is matrices needed to develop model-based control algorithms. And so you can trim the vehicle in a certain state and then send out information or specify the state of the vehicle and send out the matrices that are needed for model-based control. And then the way that it communicates here is over UDP. Typically, that's what we use, but we also have in the lab we've been also have a setup that uses serial, and it can use the MAVLink protocol, which is a common protocol for that runs over UDP or serial, but it's a certain protocol for how you package the information and what's defined within those packets. Okay, so this whole setup then, you can test this all in simulation here, graphically with a controller and the physics running, and then you can link it to the actual flight hardware. So MAVIS will also output sensors, emulated sensors like pitot-probe, IMU, GPS, those types of signals, and that can be sent to the actual flight hardware. And the controller then obviously would be converted to C or C++ to run on this onboard hardware. And so once you have this set up, then this dashed line shows how you would have a hardware in the loop simulation. And so the flight hardware, rather than getting real information from an actual pitot-probe or an IMU, is getting simulated data from the physics. And so we can test out and actually fly the hardware, on the ground in simulated environments before we actually go out to flight test. And also this hardware in the loop can still be sending out visualization of the vehicle state as well. So once that flight hardware has been tested through different simulations, then that can just be loaded directly onto the vehicle for actual flight. And all that's needed is to swap the connections from reading in simulated sensor data to actual sensor data from the actual sensors on board the vehicle. Okay, so this is the framework that we've developed, and I'm just going to walk through rapidly with this example here. This is the TRV 150 vehicle. We have not flown this in our lab. This is just an example of a vehicle, and I'm just going to walk through the process of how you do this. And I'm actually not going to talk about hardware in the loop today. I'm just going to focus on developing the model, putting that into this physics engine, and then we'll show some example visualization here of that vehicle and a few different examples and also how to link it up to the controller. Okay, so let's start off with the vehicle. Now, I have never actually seen one of these vehicles in person, and so I just went online. This is a TRV 150. I don't know much about this, and there's not a lot of information in terms of dimensions about this vehicle, but I know it has a 150-pound payload, and so that gives me an idea of the basic weight of this vehicle. And there's also some graphics of a human standing next to it. In fact, right here in PowerPoint here, this is a graphic I found online, 6-foot person standing next to the vehicle. And so based off of that, I just estimated some of these dimensions. And I'm not sure how accurate they are, and that's not really the point. The point is the process here. So based off of this, if this line is equal to 6 feet, I was able to bring over and estimate some dimensions of like rotor diameter, the body size, the length of these arms, the width of the arms. It also has these 2 motors, one for an upper rotor and one for a lower rotor on each of its arms here. And I'm going to simulate that as a single cylinder for the aerodynamic purposes, a tall cylinder, so you'll see that here. So let me jump into mockup. So mockup, like I said, is this, it's just an online sketch pad basically for rapidly sketching fixed wing or rotary vehicles. And I've already got the components sitting in here that are necessary, but let me just show you how I put those in. So if you go up to add here, you can add different geometries, box, cylinders, spheres, those types of things. And then you can also add wings and propellers. Now this example doesn't have any wings, so but let me show you how like I drop in a propeller. So it puts the propeller there. You can move it around in XYZ here. And let me just play with this propeller for a second. So with that selected, it's got some options over here where you can set the diameter. So we'll double the diameter of the propeller. We can say the number of blades. Let's set that to 5. So we've got a 5-bladed propeller there now. And you can set the hub radius, the root chord. That's probably going to be a bit larger than, that's way too big. Let's see. Let's drop that back down to, 0.2. And then the tip chord, you also can specify information about the airflow and stuff like that. So anyway, this information in our current framework is really only used to estimate the mass and inertia of the vehicle, okay? And then also the locations of the rotor thrust and propulsion properties of the rotor. Okay, so we can drag that around. We can change the orientation of that. So about the y-axis, if I want to rotate that by 45 degrees. So we've got a rotor sitting there in space. Okay, so let me just show you an example with a wing. So here's a fixed wing. Again, you can move that around, and you can add as many wings and rotors as you want and place them in different locations. You can actually link them to each other so that when you move one, it moves the other. So anyway, it's a pretty nice little framework just for sketching out a vehicle. But on the wing, let's just add, so for example, 25 degrees of sweep and maybe 20 degrees of dihedral. And so anyway, you can see what you can do with that, but it's just really simple to build out basic vehicle geometry to capture the essence of that vehicle very rapidly. Okay, so what I've done here is based off of, oh, and by the way, this is a dimensionless code. So you get to choose what each of these square sizes is. So I'm doing this all in feet. And so I'm just estimating from that drawing that the vehicle body right here is about 3 feet long and maybe about a 1.5 feet wide. And then I've estimated, the size of these arms from a cylinder that I have rotated and moved out to this location. And then I have 2 rotors, an upper and a lower rotor that I've placed here on this arm. And then, like I said, that cylinder right there representing the 2 motors that are driving those rotors. Okay, and so now that I have the basic geometry, this information, in a future version, you'll be able to go up here to File and Export to MAVIS. Previously, we used this to export to a different aerodynamic code, but we're in the process of modifying that so that it will export to MAVIS directly. I don't have that working right now, so I'm just going to show how this information gets put into a MAVIS input file. Okay, so so all of the input files to MAVIS are in a JSON format, okay? And we're going to look at this vehicle.json. This is the JSON file that defines that entire vehicle. And we're going to come back to propulsion here in a minute, but under components, every vehicle is made up of any number of components that are stuck together. And so, for example, this vehicle is made up of a body. The name of these components is arbitrary, so you can name those whatever you want, as long as it's a unique name in that in the list here. The body is of type cuboid, so that's just that rectangular prism. The location we specify, and just because of how I have my coordinate system here, I just have that body sitting at 0, 0, 0. You can change the orientation of it. Here's the length of it. So in X, Y, and Z lengths of that cuboid, and then the weight of it. Now you can actually specify either the weight or the mass or the density of the material used for that component. Okay. All right. So here's arm number 1. It's a cylinder, and this is just this cylinder coming off of here. So I've defined its orientation. It's rotated about the z-axis by 45 degrees. It's got this location. And then it has a length and a radius and a weight as well. Now each of these has a flag that you can set called include arrow. And that flag basically sets whether or not the aerodynamics of that object are included in the aerodynamics of the complete vehicle. The reason that's there is that sometimes you want to turn that off. So for example, maybe we have a battery or other electronics or something that we want to set inside of this body, and we want the mass and inertia of that component to be included, but because it's not an external object, it produces or has no effect on the aerodynamics of the vehicle. And so so you could drop another cuboid in here or whatever, or a camera. Maybe we're carrying a camera in here that we want to capture the mass of that camera, but not the or any other payload, but not the aerodynamics, because it's an internal object. Okay, so but for everything that we're using here, we're going to have include arrow set to true because these are only external objects that we're looking at. Okay, we're actually going to have 4 arms, right? So we have this is the definition of one of those arms, and then I have arm 2, 3, and 4, where the only difference really is the orientation that I've rotated it and the location that I've put those 4 other arms. And we'll check that here in just a minute. Okay, then we have 4 motors. These motors are these cylinders here that are representing the motors. And again, we're just going to have 4, although the actual vehicle has 8, but we're just capturing the aerodynamics of a cylinder sitting out here. So so we're going to have 4 of those, and those are placed and oriented correctly around the vehicle. And then we have actually 8 rotors. Now the way that I've named these are rotors 1 through 4 for the upper rotors, and then rotors 1A through 4A for the lower rotors. Okay, and there's these are basically the same things that you saw in mock-up, the same type of options that we can set. One thing we're going to see is really important is the rotation direction of the rotor. So whether it's a right-handed or a left-handed rotor, that affects the torque that the vehicle experiences, as well as some of the other forces and moments produced by that rotor. Um, okay, so each of these rotors is hooked up to a propulsion model, all right? And so there's a propulsion option. If it's a type rotor, you select, you can tell it what kind of a propulsion model you're using. And this is where we're going to go back up to the top of this file and where that propulsion model is defined. And so this one is set to prop. Let me come up here to this propulsion dictionary. And this is just a dictionary up here of a bunch of propulsion models that are very versatile actually. But I just have two examples here. One of them is a simple propulsion model where all we have is a thrust coefficient as a function of advance ratio. And so this would not be accounting for any of the torque back on the vehicle. It would just be like having this little thruster out there that doesn't produce anything except for thrust on the vehicle. So this is a very simple model. And then we've also got a default model just built into MAVIS where you can enter a pitch to diameter ratio of the propeller, and it will just estimate roughly what the torque is going to be and what the what the thrust coefficient is, the normal. There's a couple other forces of moments that are included in that as well. But so it's just off of a generic rotor. And then part of the challenge here is that manufacturers don't like to give out their information about their rotors, and so to get a really high fidelity model of this, you actually can do, but you need to know the actual pitch distribution within it. You need to know what airfoils are being used. And anyway, it's often information that's just not readily available. So we're just going to use an estimate for what a rotor would be doing out there based off of this default rotor type for this particular example. Okay, so let's come back down. So we've set that propulsion to type prop, and all of these are going to be identical. They'll all be using that same propulsion type. And then for each of them, we can also set how this rotor is controlled. And so we've got this thing called control, and that can be set to either, right now our two options are you can set that to a thrust in pounds force or to an RPM. Okay, so that means the control signal that's being sent in from your controller that's in this external controller algorithm is going to be sending in a signal as a function of time, and so we need to know, is that an RPM or is that a thrust? And if it's an RPM, then this rotor will set the RPM of that propeller and then compute the thrust that comes off of it. Or if it's thrust that's specified by that outside entity, then it will compute the actual RPM under the hood just to compute the other, like the torque and things like that coming off the rotor. So anyway, either of these can be specified. I use a little underscore here when I don't want the code to recognize a flag. And so the reason I've set this up this way is so that I can flip between RPM and thrust and just check different things by putting a little underscore, because the code is only going to recognize this keyword control. So this other keyword, it's just going to skip because it doesn't recognize it. Okay, so we set that for each of our rotors. So we got rotor 1 through 4 and then 1A through 4A. Now let me come back to the drawing here for just a second. It appears that this upper right, this upper rotor right here is a right-handed rotor. So if you stick your thumb out in the direction or up from this, then it rotates to the right. The lower rotor looks like a left-handed rotor to me, and then so it looks to me, and I think this is pretty universal, is that you basically make the two opposite each other here, both right-handed. These two would be both left-handed for the upper level, and then the lower level is just the opposite for each of those. So the right-handed is paired with the left-handed below that, and that just helps with with some of the torque and aerodynamics caused by these rotors to balance it out. Okay, so that's how I've got it set up here, where rotor 1 is a right-handed and rotor 1A, if I open this up, is a left-handed rotor, with everything else being identical except that the Z location of the second rotor is below, and the Z location of the first rotor here, the upper, is above the vehicle body. Okay, so I think that's the only difference between these two rotors, 1 and 1A. Okay, so now we've got all of our components specified, there's another dictionary within here called control effectors. And this control effectors object basically allows you to now give information about how these controls are going to be used. So for example, let me open this back up. Rotor 1 here has this control, and it can be set to RPM or thrust as the signal coming in. However, when that signal comes in, let's say that we're at 1000 RPM and all of a sudden the controller says to go to 5000 RPM. Well, there's a time delay in how long it takes us to go from 1000 RPM up to 5000 RPM. And there's also limits on what the maximum RPM could be. And so there's three things here that you can set for each of these controllers. And this basically gives you a first order lag model with limits on what this thing can do. And we're just showing this for rotors. You can do similar things for control surface deflections on wings. For an elevator deflection, aileron, rudder, you can set these magnitude, rate limits, and a time constant so that within MAVIS, it's simulating this first order lag in what's being commanded and what is actually being done by the vehicle. Okay, so for each of these control effectors, so we're going to be looking for 8 signals coming in from our control outside control algorithm, and so we can name each of those independently. So I'm calling this one throttle 1. Its parent component, so we have to link it to a component up here, is rotor 1, and then it has these magnitude limits, rate limits, and a time constant. Okay, and so and I'm just using identical values for all 8 of these, but they can be different values, and then we're just linking them to different things. So we'll have one linked to rotor 1 here, rotor 2, 3, 4, and then 1A, 2A, 3A, 4A. Okay, so that now sets up the controls that we're expecting and the limits on that. Okay, so that basically shows you how to set up this the vehicle within this MAVIS physics engine. Now let's talk about how to actually set up the simulation. So what are we going to simulate? We've got the vehicle defined. What are we actually going to simulate? So let me come over here to the actual input.json file. This input.json file is the master input file to MAVIS. And you can name it whatever you want. When you run it, you just pass in the name of the input file that it should read. And it has a few different dictionaries in it. This first dictionary is just a simulation dictionary that gives some really broad information about the simulation. So what's the beginning time, ending time? You can hard code a time step in there if you don't want it running real time. What's the ground altitude? This verbose flag if you want to see a bunch of output or just a little bit of output. There's also printing and saving rates that you can set, and a pulse rate, and then connections. How are connections handled? So what UDP ports are we looking for information on? What UDP ports or serial ports or whatever are we sending information or read write to other codes? So for example, the graphics, we need to know how we're communicating with the graphics and how we're communicating with the controls algorithms. So there's also an atmosphere dictionary. What atmosphere are we flying in? And there's a standard atmosphere built into there, density as a function of altitude. There's also turbulence or gusts. We've got a Dryden gust model in there. I'll demonstrate here in a moment. You can turn on and off. And then here's the vehicle properties. So the actual properties of the vehicle are read from this vehicle.json file that we just covered here. And then you can set the initial state of that vehicle. So there's a bunch of information that you set for that vehicle, as well as initial information for the control effectors. So this is where the values of the control effectors are going to start at, and they will remain here until it reads any information on the port that we specified up here in this connections dictionary. If we get a signal from an outside controller, then it will change and update those 8 values, but they will be initialized to this. And then there's an analysis dictionary where it can do other things, like it can draw the STL, it can print the aerodynamics at the current state, it can export linear state space model. So this is where I was saying, once you set it to this initial condition, then it can export the linear state space model that's needed for a model-based control if needed. Okay, so that's the basic input files, and there's a bunch more options that I'm not going over in here, but this is just the basic setup. So let's run this and see what happens. So we've got these control effectors. The total weight of this vehicle, I set these, if you add up all the weights of the motors and the arms and the rotors and the body itself, I have this set to weigh 100 pounds exactly, okay? And I don't know what the actual vehicle weighs, but this is just for demonstration purposes. So we've got this weighing 100 pounds. That means that each of the control effectors here, each of these motors has to be putting out a thrust of 12.5 pounds. So each of these rotors, I've got their control element set to thrust. So it's expecting a thrust value in pounds force. So I'm going to initialize and say, okay, at the start, you're each putting out 12.5 pounds, and it will compute the actual RPM for each of those rotors in order to output that much thrust. Okay, so before we run this, let me actually generate, I'm going to run, let's see, let me drag this up here. Okay, so I'm going to run MAVIS input, input.json. Let me clear this so that we're, okay, when I run this, because I had this analysis thing turned on, it drew an STL of the object. So let's start by just checking the STL of that object. So it drew, in this folder that we're operating in, it drew this vehicle.stl. And so I want to compare this STL to what we had over here in mockup. So I'm just going to drag this STL in here. And so it drops it on there. And so now we've got the representation inside of MAVIS in gray here of what this vehicle looks like, and that's dropped on top of what I had already here in mockup. And let me just drag this off of here so you can see there's actually two vehicles. So that was my original drawing, and this is the new one that I just brought in. And I like to do this just to double check to make sure I have all the dimensions in there correctly, things positioned, and that it all looks reasonable. Okay, so there's our vehicle STL. And then that STL, I won't demonstrate it here, but we've got a script that will convert the STL file into something that is much, it just takes a moment, but it'll take this STL file and convert it into a type of VTK file that the graphics can read. The reason that this is important is because there's actually a whole lot of redundant information in an STL file, and we want to be able to display this vehicle as rapidly as possible. And so it basically deletes out all redundant information without lowering any fidelity of the actual geometry. So let me actually bring this over and look at a wireframe version of it. So you can see this wireframe version of this vehicle. So we're going to see every line that we see on here in the graphics when we visualize this in MAVIS, but there's a whole bunch of redundant lines in an STL, just how they're defined. And so that code is just a Python script that will convert this from STL to this VTK file. Okay, so we're now ready to run this. So I'm going to run this viewer so we can just see what's happening. So it opens up that VTK file so we can see what the vehicle looks like. And now we're going to watch this vehicle as we run MAVIS down here, and it will run for a whole minute. Okay, so we initialize this in the input file to start at 100 feet in altitude. On the right hand side here is altitude, and this is our velocity over here. Now we set this to be perfectly trimmed. So each of these rotors is outputting 12.5 pounds of thrust. It's choosing the RPM. All of the torques are perfectly canceling, and so it turns out this vehicle will sit here and hover forever until machine precision adds up. We get enough air for it to start moving, but that'll take a while. So this is just perfectly trimmed as we have it. So that's kind of boring. Let's see what happens if we set one of these thrusts to just something slightly higher. So 12.51 pounds instead of 12.5. So I'm going to kill that, and let me pull up the graphics again. I'm going to rerun this, and now this front right rotor, upper one, is just putting out 0.01 pounds more than every other rotor on there. So you can see that it starts to rotate here. We're actually dropping in altitude, and we're picking up speed here, and eventually we'll will flip over and fly through the ground. Okay, so now we're not looking, well, it is looking actually for an outside controller to control this, but because it's not getting any information, it's just going to keep things constant for now, so it's just keeping these values at 12.5 throughout this full simulation. Let me show one other example here. What if we switch just this front top propeller from a right-handed to a left-handed propeller? Okay, so we had everything perfectly balanced with our right hand and left hand, and now we're going to rerun this just by switching the that propeller. So this propeller now is a left-handed instead of right-handed, and it just so happens that all of our mass is perfectly distributed in this horizontal plane. And so first, all we're experiencing is this torque, but eventually we'll get enough speed here that the entire system will go unstable. So anyway, and that's just as a result of that, the direction of the propeller, whether that's right or left-handed. Okay. All right. So this is an example of how you can send in a vehicle and actually run it. We can view it. I'm not actually going to demonstrate how to link that up to a controller today, although it's very simple. I have a colleague here at Utah State. I have a colleague at University of Michigan that has a few students using this framework, and they were able to link to it very rapidly because MATLAB, both of them are using MATLAB, although you can, we actually internally have hooked up C++ and I think maybe even Python to this as well. But anyway, once you get the control set up to talk over serial or UDP or whatever connection you're going to use, it's very simple to pass information back and forth. So, okay, let me demonstrate turbulence here for just a minute. And I'm actually going to do that on a different vehicle because there's a couple options that I think are important to understand. So we didn't know anything about this vehicle, and so we just put in the geometry. But let's say that you actually have a lot more information about a vehicle. All right, so I'm going to show this example of an F-16. Now we've this is actually an example that I use for a class that I teach on flight simulation, but you can get this information from a report that was published by NASA in 1979 of some basic aerodynamics about an F-16 that they put in a scaled model of an F-16 in a wind tunnel. So in this situation, the components here is made of just one, well, I actually have two things here. I've got thrust for an engine, so I've got an engine component, but the airframe is just a single component because we actually know a lot about that component. We know all of the inertia properties of that component, which we can read in there directly. We know the weight of that, and then we can actually specify the aerodynamics of that vehicle using two different methods. And so let me just demonstrate those. But we know those. That's come from wind tunnel data or CFD or whatever. If you have an aerodynamic model, that can be read in here directly. So the MAVIS is not just estimating that based off of simple geometries of the vehicle. So let me go into F-16 aero. That's what this is saying, is that the aerodynamics are specified in F-16 aero. So if I pull that up, there's two different ways that you can specify the aerodynamics in here. First of all, you specify a reference area for your coefficients, and then a stall model. You can turn that on and off. But then you can either read in a database, and this is just an example, but you can read in a whole bunch of CSV files. That's how the NASA data is published. It's in it's probably 10 different data sets that basically get added together. And so you can list out all of those data sets and add all of those effects together. Or you can also define custom variables that are functions of things that the simulation, keywords that the simulation recognizes. So for example, angle of attack, side slip angle, PQ and R, rotation rates, and then the names of any of your control surfaces. Now this F-16, we've got an aileron and a rudder. I can go back to that vehicle and show you that the control effectors, I named those. These names are arbitrary, but of course they're well known. Aileron, elevator, rudder, and throttle. So these are the four control components that it will be looking for. And so in the aerodynamics can be a function of those. So we've got aileron here, rudder here, and actually it can be a polynomial function of these things. So The lift, side force, drag, roll, pitch, and yaw moments can be polynomial functions of any of the keywords that it recognizes. And I can go into more detail on this at another time, but basically these keywords here get parsed out, and it figures out what the polynomial equation is for this particular parameter, and based off of these keywords here. And then so like I said, you can put in these coefficients. You can say whether those are in the wind axis or the body axis, things like that. So it's pretty powerful in terms of different types of aerodynamic models that can just be read in directly. Like I said, you can either just bring it in as a data set if you have a big lookup table, or if you have polynomial equations that have been fit to this data, then you can bring those in directly. Okay, so let me just demonstrate this now with, I'm actually going to show an F-18 landing on a carrier. Okay, so here's this F-18 landing on a carrier, and this F-18 is actually going to use the F-16 aerodynamics. So I don't have an aerodynamic model for an F-18, but I've got this setup with an F-18, and so now I'm going to start. So we've got our visualization here. We're going to run the F-16, but let me real quick go to the input file for the F-16 and see if we are okay. So I'm going to turn off turbulence to start with. So when I run this, there will be no turbulence, and we'll just see. Okay, so this has been trimmed to basically be in a descent path towards that carrier and to land on the deck, and it's not capturing any turbulence. It's perfectly trimmed, so it's just gonna basically hit the deck there, really close to where it's supposed to. And there's no collision right now modeling in this, so it doesn't know that it actually hit the deck, but that was right on target. So now I'm going to turn on turbulence. You do that by just specifying the type of turbulence here and then the intensity. We're just going to put on light turbulence right now, and let me rerun this, and we'll actually run this a few times. Let me pull this up there and bring this down here. Okay, so you can see that moving around there. So with that turbulence, we took a very different path. And because I have this set, let me just jump over here for a second. This seed, you can set that to auto. And that means that every time it runs, it's using a different set of random variables that are being used as a seed for the turbulence. Or you can set it to a repeatable value, and if that's the case, then you can rerun the same turbulence over and over again if you're trying to. That's helpful for debugging things. If you need turbulence in there, but you want it to be repeatable turbulence every single time. So you can see how easily this can be set up to run a Monte Carlo simulation of where we're going to hit the deck based off of just a Dryden turbulence model, if the vehicle were perfectly trimmed to hit the deck in the right place. Okay, let me just come back here to this overview. So I've demonstrated how you walk through this process from a simulation standpoint. Again, in our lab, we've hooked this up to hardware in the loop, which I didn't demonstrate here. Controllers are very simple to plug in. One thing I guess I just want to mention at the end here is that as a lab, we kind of specialize in writing aerodynamic and simulation software, and we've done that for many years. And one thing that has become apparent to me in the last year or so is that it's really challenging for us to develop software that is truly useful to outside entities in a sustainable manner because of the turnover of students that I work with, and also because of our focus on fundamental research within the university. It's hard to justify some of the software upgrades and updates and things. So we are considering, myself along with a couple others are considering spinning off an outside organization or company that could sustain some of this software that would be of more use to the Department of Defense, other universities, or other organizations that need something like this. Anyway, so if you have questions about that, feel free to reach out to me, And with any questions about this framework and whether it could be useful to you, I'd love to chat with you more. Thanks.